It didn't work.
Okay, good morning. I'm in trouble with the projectors, but we don't need them here initially. Today we're actually going to talk about transformers. So last time we talked about these general problems, Faradays Law, where you can have induced voltage either due to time-varying field or the time-varying interaction between the surface of a loop and the field, which could be due to actually the loop changing in size or actually rotating the loop in the field will change that intercepted surface area. So today we're actually going to talk about, you'll see we'll get to some formulas that should be familiar from circuits. Because today we're going to talk about just the stationary loop case. And on Friday we'll look at the moving loop case and the stationary field. So we're going to consider the loop in the XY plane. So that means our normal is either plus or minus Z directed. And of course, we've got to figure that out. But so if you can imagine this loop X, Y, and then Z would be coming out of the board. And we're going to let our B field have an arbitrary direction. I'm just going to call B hat and be time varying, but not varying in space. So if you remember, if we looked at the solid core solenoid case, and the field was constant across the cross section of the solenoid. For toroidal solenoid, it does vary with distance from the center, but even there, it's a pretty good approximation. It can be treated as being spatially constant, but we're going to allow here time variation in the B field. So it's time varying only, no spatial variation. So we can choose a VT polarity, and this can be done arbitrarily. Well, at least you have two choices. either positive on the left or positive on the right. I just chose positive on the left. Now, once you make that choice for the polarity of the voltage, though, all the other directions are fixed. So we take our loop contour then to be, and our current to be directed from the negative terminal of VT through the loop to the positive terminal, not across the resistor. Remember, this would be the direction for if we treated the loop as a source, right? So, and then that would be the direction through the resistance, the current direction through the resistance with positive on the left and the negative on the right. If I reverse the polarity, the current through the resistance would actually be flowing in the opposite direction. Now, once we fix that contour, though, that fixes our normal to the surface as pointing in the plus Z direction. So if I had chosen the opposite polarity for VT, then N would be in the negative Z direction because our contour would have been going, would have been a clockwise contour instead of a counterclockwise. But then Faraday's law says that the induced voltage is the number of loops. Here I've only got one loop. The number of loops times the time times the derivative of the flux through the loop. Now the negative sign accounts for the fact that the induced voltage, and correspondingly, if we have current, the induced current would set up an induced field that opposes changes in the flux. So we'll talk a little bit more about that. But this is Faraday's law. So our flux equation is B dot ds. For ds now, I'm going to write it in terms of n still. It's n hat times our differential surface element. But plugging my expressions in here, for B, it's B hat BT dot N hat DS for minus B hat dot N hat. In this particular case, N hat is constant. My loop is flat in the plane, so N hat is constant over the entire surface. It's the, I don't have to choose that simple surface, but usually we choose the simplest possible surface. So N is constant over this simple surface, so I can pull that dot product out. And BT doesn't vary over the surface either. I said it's constant with regard to spatial variation, so I can actually pull it out. And I'm just left with this surface integral, which is just the area of the loop. So what I end up with for my final result here, it's where A is the loop area. Seems like kind of an odd way to write it, but this B dot NA kind of represents the flux dependent, the flux through the surface intercepted by the surface. And that depends on, you know, the angle between the surface and the field. So if they're aligned, so that all my flux is coming, is in the n direction, is coming through my loop, then this is a maximum. But if my loop is at 90 degrees, remember if my loop is in the same plane as the field, N, which is the normal to the loop, would be perpendicular to the field. So if the loop though is turned so that none of the field lines are actually going through the loop, then this would N hat would be at 90 degrees to B, and this would be 0. So this term in parentheses kind of represents the amount of flux captured by the loop. But it also indicates that the loop shape here is irrelevant when the flux isn't varying with spatial distance. This is just the area of the loop here. I didn't have to, it would be the same whether it's a circle, a rectangle, any sort of odd shape. Vt is also proportional to the time rate of change of the flux. So if the flux is constant, not changing, we don't get an induced voltage. So that's another thing that's important. The flux has to be changing in order to get the induced voltage. Finally, the current is Vt over R, where this R is that's important to realize that I won't have a current unless I have a load across those loop terminals. Right? I will always have an induced voltage, but not necessarily a current. Now, the way I've set this up would be coming out of the board. Notice with the minus sign here, okay, that if B is increasing, my voltage and my current would both be negative. If B is increasing, this is going to be a positive, right? The time rate of change would be positive. And so Vt and my current would be negative, which means if Bt is increasing, getting larger coming out of the board, I is actually flowing in the opposite direction. And so my induced field would be in the negative Z direction, opposing the increase. If Bt is decreasing, still Z directed, but a time rate of change such that it's decreasing, getting smaller, then this derivative would be negative. I have the negative of a negative. Vt and the current would both be positive, as shown. And so the induced field by the current would be Z directed in the same direction as B. So the induced field is always directed so that it opposes changes in the B field. Okay, if the B field's trying to decrease, the induced field will be aiding the B field to keep it from decreasing. If the impressed B field is increasing, the induced field will be opposite to the impressed field to fight the increase. So maybe either in the same direction as B or opposite to B, again, depending on the rate of change of B. So here's a simple example. That would apply in this case. So I'm assuming that the B field is sinusoidally varying, and I'm assuming that we've got a circular loop of radius A, and that it's aligned with the field. So the perpendicular to the surface is in the same direction as my B field, so my loop captures the maximum amount of flux. Then the partial derivative of B with respect to time, here I'm getting a 2 pi F0 B0. My sine becomes a cosine. So that's the partial derivative of the V field. And my VT then is now minus the area times that. Okay, so for a circular loop, I'll pick up a minus. I'll get a 2 pi squared A squared F0 B0 cosine of 2 pi F0 T. So the induced voltage would be sinusoidally varying. And then, of course, the corresponding current would just be minus 2 pi squared A squared F0 B0 over R. Would also be sinusoidally varying with the, and in phase with the current if the load is a resistor. You know, if the load is actually something else, then there'd be a phase difference between the current voltage. So I can't get the projector to show. If you can, you've got your books. I'll turn this monitor around. Best I can do, unfortunately. Figure 8.6. I'm going to take the time to do all this. I'll have to, since I can't see it, I'll have to. Reference it. Pull up my book. Okay. So how do we get this time varying field? Well, one way is to actually have 2 loops. So that brings us to the next topic, where we'll talk about transformers. And we'll end up with the same equations that you had back in circuits 2 when you were discussing transformers. But now we'll get those equations from magnetic field principles. Okay, so if you look at that figure 8.6, B2 would be minus the number of turns in the second coil times the time variation times the rate of change of the flux through the second coil. So this is a simple case where we've got 2 coils wound on the same core, but the winding directions are really important here. So I wanted to try and project this figure so we could talk about it more. But this is minus into partial derivative with respect to time of B dot minus Z BS. So that should be in agreement with the assumed VT polarity, V2 polarity on the bottom coil. And remember, we're thinking of this thing as a V2 as a generator. It's the induced voltage, so current would be coming out of the positive terminal. So yeah. So this, and then, so that would make the surface area actually in the plus C direction. So where's my minus sign coming from? I'm hoping that's coming from the other one. If you look closely then at the other coil, assuming V1 is positive, now we treat that other coil actually as a load. So current would be flowing into the top terminal, and then the flux would be negative Z directed in that case. So actually, the negative sign here actually goes, the B field is actually going to be in the negative Z direction, and my surface area for the second one is actually positive Z directed. So this is from that figure. Now in the second figure, we've moved the source onto the bottom coil, and we're going to adjust V2 until V is the same as in the previous figure. And then so V1 would then be minus N1 partial with respect to T of the flux V1, or minus N1 partial derivative of B dot Z hat ds. That one. And so in that case, I said this wrong previously. So in the figure 8.6, okay, and the top coil is a load, so current flows into the plus terminal, and the B field would be minus Z directed. In the second coil, that's where we have our voltage induced, and so my current actually flows into the minus terminal around the loops out the plus terminal. So when I do that, the surface area would be negative Z directed, like this. And I haven't taken into account the B field. It would also be, if V1 is positive, it would also be minus Z directed. Now when I switch the cases, again, the surface area direction here depends on my assumed polarity for V1. So V1, I've assumed it's positive at the top. So current flowing from the negative terminal in the loops out the positive terminal. So my thumb in the direction of current, curl my fingers up inside the coil. In that case, that normal is positive Z directed. But I've adjusted V2 so that I've got the same B in both of these. So, but by rewriting V1, moving the negative sign inside, I get N1 partial with respect to T of S B dot minus Z hat ds. So these two integrals actually are the same. The time derivative of those integrals are the same, actually, by moving that minus sign inside. So I can solve for this time derivative of this integral from this first equation, and it's going to be minus V2 over N2. So if I make that substitution, minus V2 over N2, or that leads to V1 is minus N1 over N2 V2 is the relationship. I get a direct relationship between the voltages. It depends on nothing more than the turns ratio. I am also relying on the fact that the core has the same cross-sectional area for both coils, so the surface interval is the same in both of these cases. Now, if you go through this, if you reverse the direction of one winding, you get V1 is plus N1 over N2 V2. So the magnitude's the same, but depending on the winding direction, you'll get either a plus or minus relationship between these two. Okay, so generally though, V1 is plus or minus N1 over N2 V2. Now, I've always found it, this is one way of stating the transformer relationship. I've always found it easier to remember using, this is what I have committed to memory. The voltage per loop is the same in both the primary and secondary coils. So V1 over N1 is plus or minus V2 over N2. That's how I've always remembered it. Okay. So, but you know, it's equivalent. So just cross multiply to get either result. So typically, if you've got this figure in your book, so typically a toroidal coil would be used. Okay, and again, you could assume either polarity for V2 here, and so a toroidal coil would be used to keep the flux actually confined to the core. But you know, here they've shown V2 as being positive at the bottom. So the question becomes, you know, what do we use the minus sign or plus sign for the relationship? And that depends on the winding of both coils. And so the procedures like this, and if you start in the primary coil, you treat the primary coil as a load. So current flowing into the plus terminal of the coil. Okay. Whereas in the secondary, you assume the current is flowing out of the plus terminal. It flows from the minus around through the coil out the plus terminal. So, but looking at the primary coil here, assuming current flowing into that positive terminal based on that winding. So it starts out going on the back side. So based on that, put my thumb in that direction of the current, curl my fingers inside the coil, the B field created by the primary would be counterclockwise directed. Everyone see that? So now, based on the assumed polarity in the V2 field, we would say that in this case, our current flows from the minus terminal around to the plus terminal. And so here we've got the impressed B field on this secondary coil is counterclockwise. So is that consistent then with the sign here in the second one? And we go back to Faraday's law here, that increases here should create increasing V field here should create a VT that is the negative of the increasing flux. So our minus sign here, put our thumb in that direction. Our current would be our induced field would be in the opposite direction. And that's consistent there. So in that case, since so visualize the source connected to the primary. We did that. Determine the flux direction from the current flowing from plus to minus, to treat that as a load. And then imagine opposing flux in the secondary and corresponding current direction, with the current flowing from minus to plus. Okay. And then if polarity matches the polarity assigned, the secondary, use the plus, which is correct. Otherwise, use the minus sign. So in that particular figure, it would be the plus sign. But if either winding were reversed, or the source polarity were reversed, or assumed secondary polarity would be reversed, we get a minus sign. So And you may remember this relationship from back in circuits 2 when you look at transformers. And we'll talk about the convention you used there was a little bit different. For transformers, you didn't actually worry about the winding directions to try and figure out the polarity. Instead, you used something called the dot convention. You remember that? Okay. But let's also look at some other relationships. So the primary side of the transformer is the side that has the source attached to it. The secondary side is the side that has the load. So this is the convention he uses in this textbook. This is the same that was used in circuits. V1 is voltage across the primary. I1 is the current entering the primary. On the secondary, we have a load called ZL. V2 is the voltage across the secondary coil in the transformer. Now, in your electromagnetics book, he defines I2 in that direction. Now, in your circuits book, it was actually in the opposite direction, so I'll talk about that. But I just want to be consistent right now for with the notation in this text. So, but from power conservation, the power being delivered to the primary is the voltage times the current. The power that should be equal to the power being delivered to the load. But with I2 being defined as coming into the secondary, if I2 were reversed, then the power being delivered would be I2 V2. But with I2 as shown, I need this minus sign there to represent the power being absorbed by the load. Now this equation is assuming that the transformer doesn't use any power itself. That's not quite true. Any practical transformer will actually, due to the resistivity in the coils, will actually convert some of the input electrical energy to heat. So transformers aren't 100% efficient. But this is assuming that they are, so this is for the ideal transformer case. Okay. Or so from this we can derive a relationship between I1 and I2. It's equal to minus V2 over V1, which is minus, and I have plus or minus N2 over N1. So it would be minus or plus N2 over N1. Now this minus sign doesn't come from any winding direction or anything like that. This comes from actually defining I2 that's going into the secondary. But with this convention, if V1 over V2 is, if that relationship is a negative, then I1 over I2 would have the positive. It's just reversed. Okay. So if we have a positive negative for voltages, we'll have a negative positive for the currents. So, or in terms of the ratio of the secondary voltages to the primary voltage and the secondary current to the primary current, and V2 over V1 is plus or minus N2 over N1, but I2 over I1 is minus or plus N1 over N2. So if the voltage goes up, if the secondary voltage is higher than the primary voltage, that's if N2 is greater than N1, the secondary current will go down by the same factor. So if the secondary voltage is higher than the input voltage by a factor of 10, the secondary current will be smaller than the primary current by a factor of 10. That's power conservation. If we define I2 in the opposite direction, like you did in your circuits, you would have gotten the same sign for both of these. It would have been plus or minus relationship there and plus or minus here. So this sign reversal is because we find I2 is going in. Okay, so this is the relationship between the currents. You can also get a direct relationship between the impedance seen looking into the primary. So we could replace the transformer and the load as far as the source is concerned with this equivalent impedance. That's what this Z1 represents. And it's the ratio of that voltage to that current. So I could replace everything to the right of this pair of terminals with this Z1 impedance. Z1 is directly related to Z2 in the turns ratio, because V1 is plus or minus N1 over N2 V2, and I1 is minus or plus N2 over N1 I2, or I get minus N1 over N2 squared times V2 over I2. Okay, and again, I got to be a little careful with my sign convention. V2 over I2, if I2 were flowing to the right, that would be equal to the load impedance. But because I've defined it going to the left here, I pick up another minus sign, and this becomes N1 over N2 squared times the load impedance. So this is another result and another way to analyze transformers. So the transformer makes the load impedance look either larger or smaller, but if it's inductive, it still looks like an inductor. If it's resistive, it still looks like a resistor. If it's capacitive, it still looks like a capacitance, but it's multiplied by, the ratio of the turns ratios squared. So if it's what's called a step-up transformer, where N2 is greater than N1, then the impedance looking into the primary is smaller than the load impedance. We see a smaller load impedance. If it's a step-down transformer, where N2 is smaller than N1, then this ratio is greater than 1. And impedance looking into the primary would be a lot larger than the load impedance. So just the other way this is written is Z1 over ZL is equal to N1 over N2 squared. Okay, so let's go back and talk a little bit about the equations you saw in circuits and dot convention. So there was a transformer and all the circuits problems. And I'm just going to show load resistance here, V2. And here in circuits, we showed I2 going in this direction. And I'll put a source resistance in here, VS, V1. So, if you don't know, from our standpoint, we have to actually look at the windings to determine whether this is plus or minus. And most circuit schematics, the schematics aren't detailed enough that they'll allow you to do that, to actually look at the windings. It's not convenient from a schematic standpoint to be that detailed with and it gives some sort of 3D representation of the actual transformer windings. So the convention is to actually put a dot at the terminals representing with the assumed polarities. So with assumed positive at dot for both voltages, then V1 over N1 is equal to plus V2 over N2, or V2 over V1 is plus N2 over N1. The dot convention just helped you determine whether you have this plus relationship or this minus relationship. Now, so a couple things here, often if you're given this, a circuit, you're free to pick the polarities often. You can pick V2 to have whatever polarity you want. Same may be true for V1. So it's usually convenient to put the assumed plus terminal at the dots. Don't have to do that. If I'd chosen V2 so it was positive at the bottom, then I'd have a minus sign in here. If I'd chosen V2 like this, but the dot here was actually at the bottom, again, I'd have to use the minus sign. I get the plus sign when I have both pluses here at the dot. Now, if both dots were reversed, it would still be a plus relationship. If I had the dots at both assumed negative terminals, okay. But if I have one dot at a plus and one dot at a minus, then I need the minus sign in here. Okay, so that's all that dot convention did for you is took away the details about the winding directions and the coils and allowed you to get the right convention for the sign. It could be either plus or negative. Okay. The other thing is with current directions, as shown, the power relationship was I1 V1 is I2 over V2. And so I2 over I1 was N1 over N2. Again, this though comes from my power convention. Whereas in our textbook, he's got a minus sign in there because he has I2 going in the other direction. My recommendation is the only two formulas you need are, actually, this is the one I have memorized. This one has a plus or minus in it, depending on the dot convention. So the voltage per loop is the same in both the and the. So if this is 10 volts over 100 loops, here if you have 200 loops, okay, you're going to have 20 volts. 10 over 100 would have to be the same as 20 over 200, right? So the voltage per loop is the same in both the primary and secondary. So I remember that one. And whether this is plus or minus is determined by the dot convention. The other one, the only other formula you need is this power convention formula. And again, this is the one we used in circuits. He has a minus sign in the one over there, and that's because the current is in a different direction, the I2 current. I prefer the circuits convention. Power delivered to the primary, power delivered to a load. But you could choose to do it differently. If you do, if you reverse I2, you need to throw a minus sign in there. From these two formulas, you can get all those other relationships for I1 and I2, or Z1 related to the load impedance. They all follow immediately from these. The other thing that terminology you remember from circuits is, we talk about step up and step down transformers. That refers to voltages. So if if N2 is greater than N1, this ratio is greater than 1, which means V2 has got to be greater than V1. So that's a step up transformer. That means the secondary current has to be smaller than the primary current, though. So, but the step up and step down refer to the voltage ratios and also the turns ratios. You know, if the number of turns in the secondary is greater than the number of turns in the primary, it's a step up. If the number of turns in the primary is smaller than the number of turns, if the number of turns in the secondary is smaller than the number of turns in the primary, then it's a step down. The secondary voltage would be smaller than the primary voltage. The secondary current, though, would be larger than the primary current. So another question that students ask is, a transformer obviously provides voltage amplification, right? I can use a transformer to get voltage amplification. Right? So why do I need transistors? And transistors, one of the big applications of transistors is they provide voltage amplification. Can't I just always use a transformer? Transistors do something else. Transistors actually convert DC power to AC power. You're hooking up transistors to DC power supplies. Transistors actually have power gain. Okay. The AC power delivered to your load from a transistor would be a lot larger than the AC power coming into the transistor. Again, power is conserved. You're stealing power from your DC supply and converting that to AC power. But transistors actually provide power gain where transformers do not. Transformers can provide voltage gain, but if they're providing voltage gain, the current is less. The output power for a transistor at best is the same as for a transformer is the same as the input power. For practical transformers, the output power is actually always less than the input power because there is some loss in the transformer itself. But transistors actually provide power gain, increase in both voltage and current. All right, that's it for today. So.